the topic of today and in 2 weeks is ventilation of the lung and gas exchange in the lung. We will look at the lung from an engineering viewpoint. We are engineers. I'm not a medical doctor, so I cannot say much more about, let's say, clinical issues related to the lung, but I think when we abstract this system into terms which can be described mathematically, it becomes like a technical system which we can analyze. And we would like to do that also, of course, using fluid dynamics and other mathematical tools. The first thing I will do, I will give you an intro, just a basic physiological facts about the lung, which we have to know. And then the main part today, we will talk about how the air gets distributed in our chest. So we have essentially two things which we have to do. So we have to make sure that the exchange area over which gas is exchanged is large enough that we can work efficiently, that we can run and do all crazy things which require power. And the second thing is, of course, how that gas exchange then occurs. So the first thing is really distributing the air to the volume in a way which is basically using that volume optimally. That's the topic of today. And next time we are thinking about how the gas exchange really works. Okay, so let me then start with this kind of introduction to the physiology of the lung, very briefly. And I also want to mention here that José Snitzman, he's nowadays a professor in Israel at the Technion, and he works on biofluid mechanics and bio-related engineering. And he was a PhD student at our institute, and then he basically puts the material together, which is the basis for this lecture. So I created these slides myself, but the content is based on his notes, which he made when he taught this lecture. And in this context, I want to mention that next week on Wednesday, he's going to visit and giving a talk at our colloquium for thermofluid. That's always at 4:15 on Wednesday. So you're of course welcome to attend this talk. It is at 4:15 p.m. in MLH 44. So again, MLH 44, 4:15 p.m. Next week on Wednesday. Okay, so the outline of this part of the course is first a description of the human lung. So it's more like a minimal physiological background which we should know. Then we will talk about the ventilation. I said that's basically about how the air, of course, which carries the oxygen, gets distributed in the volume which we have, where it's basically our chest, how it gets optimally distributed. And that happens in the kind of upper part, so in the lower generation branches of the lung tree. And then the next topic would be basically further into the lung, so deeper in the lung, their air exchange, and so basically not air, oxygen and CO2 exchange occur. And that is a different topic which we have to discuss, how that can be worked out most efficiently. And actually, it's quite surprising when we formulate optimization problems based on some optimization cost functions and constraints. The result of this little mathematical exercise is actually quite interesting, because the result is very close to what nature really did. And that's I think it's very nice that somehow by trial and error, what evolution essentially is, it has found essentially the optimum which we are calculating mathematically. Okay, so here, this is a snapshot from this basically tool, which is called BioDigital Human. Who knows that tool already? It's a quite cool tool. I will just give you a quick tour through it. You can basically turn on and off different systems and then focus in where you want to see more. And this is basically created like that. So what we see here is essentially the bronchial tree. And you can already see here, it is basically a binary tree. So we see here branches, and then we have different generations. Of course, this is a very rough kind of 3D model which was put into this tool. But then we have this red part that would be basically identify as the lung. And this is an agglomeration of about 300 million alveoli. These are little, almost like little bubbles. So these bubbles, they have a very, very thin membrane. And that's where basically the air which we inhale gets in contact with. And in these membranes, there are little capillaries. So there, the blood basically gets enriched with oxygen, and CO2 is basically taken out of the lung and carried away. That's basically, other way around, of course, it's taken out of the bloodstream and taken away when we exhale. Okay, so this is just again, kind of giving you an idea about this bronchial tree. And now I would like to dive quickly into this, this app. Okay, so this you find when you just Google biodigital human, and then you get to this tool. It's there's a free version, and then when you look at different systems, now we can basically look here at the layers, and should see now the layers. Okay. So here, sorry, that's I was pressing the wrong button. You don't have to push layers. You have to choose the anatomy tree. And now we can turn off some systems. So for example, we don't want to see the muscular system. We can just turn it off. Then we also would like to turn off the skeletal system. It's just in our way. And then there are many other systems which we don't know. Of course, the respiratory system we need. We don't need this one. We can turn off nervous system. We can turn off the digestive system. We can turn off the connective tissues. And the cardiovascular system I would like to keep in. And now I can go and essentially zoom in. You can basically just navigate. It's almost like moving around in Google Earth. It's now just not Google Earth, it's a human, but essentially the same thing. And now we can see also that the heart is really embedded between these two lung wings. I think it's good to know a little bit what kind of the real thing look like. And this is all scaled, so it's really in the correct spatial relations to the other organs and whatever. Okay, so we have here the heart, and it basically is enclosed by these two wings. And now I turn off the cardiovascular system. Basically, then we don't see the heart anymore. So now we are really almost focusing on the lung. And now let me just remove this thing here. I can just click on it and say delete. So see here, this basically, I've now removed the alveoli. Essentially, this is the part which makes this red color. These are these little bubbles, these 300 million bubbles, which I was mentioning. We will talk more about them. And then we can see again this nice tree. And obviously, there are some things which we can already observe qualitatively. That's the lowest generation. We call it generation 0. And then we have generation 1. And so on. And of course, there are always like 2 to the power of a number of generations, branches at that level, because it's a binary tree. We can see that the branches become narrower when we go deeper into the lung, and they also become shorter. That's going to be an important issue. Something else what we can see as well in this very, very simplified visualization is that the lower generation branches here, these trachea, for example, the first one, it doesn't have these red parts around it. So there is no gas exchange at that level. Gas exchange only starts very deep in the lung. That's also something which we will see more clearly soon. Okay, so that just should give you kind of a rough idea how physiologically we have to imagine what we are discussing in this lecture here. Good. So I think that's clear. I mean, please always interrupt me if there is some question. And if it's too much about clinical issues, then I'm not going to be the right person to answer, but I hope I can answer the questions which are related to the engineering part, which we are discussing here. Huh? Good, then let's continue. So with the description of the human lung. And I would like to again show this kind of schematic here. It's of course not as realistic as the one which we have just discussed before, because for example, these little bubbles which we see here, these are these alveoli. So these membranes which are providing an interface between the air and the bloodstream. They are, compared to the scale here, much smaller. So we couldn't identify at that visual scale, we couldn't identify them as an individual bubble. So they are in the order of 100 to 500 microns in diameter. So here they are drawn much larger. But we can see that, yeah, we have the trachea, that's the first branch, and we have the next generation, and up to about generation 15, 16, it's only a rigid system of tubes. So there is no exchange between the air and the bloodstream. That starts only deeper, and the number of generations in average is about 23. It is not exactly symmetric, so there are endpoints. We call them alveolar sacs. These are alveoles, and the endpoints are like the leaves of a tree or the alveolar sacs. They can go up to about generation 30. It's about between generation 18 and 30, so in average about 23. Okay, I said that's the bronchial tree. We have here the alveoli, diameters, as I said, about 100 microns up to about 0.5 millimeter. Just another sketch here. Actually, this is basically now showing not the alveoli, it shows the capillaries, because we need to have this exchange with the bloodstream. So we know that we have two circuits. So we have the pulmonary circuit and the systemic circuit. And when the heart pumps, it pumps blood, which is oxygen lean into the pulmonary circuit, and then it gets enriched with oxygen in the lung and goes back into the heart, and then it goes into the systemic cycle. And here what we see is in blue, it's the arteries, and in red, the veins. So now the respiratory function, I think it's clear. There is a gas exchange, or that's the whole purpose of the lung, is a gas exchange between the air, which basically enters the lung, and the bloodstream, which basically goes through these little capillaries here, which actually are embedded in these membranes of the alveoli, which we will see very nicely soon. Okay, there is on one hand CO2, also oxygen diffusion into the capillaries, and CO2 diffusion into the alveoli. So they're essentially the product of the chemical reactions of the metabolism basically gets taken out of the system. So what we are interested in is the general geometry. Okay, roughly we can say already from what we have discussed and seen, it's a binary tree, okay? Dichotomous tree, branching tree, so we have nodes, and then at every node we have two daughter branches, and that's basically the rough architecture. Now, of course, there is much more. It's also a question how long are the daughter branches and how thick are the daughter branches in relation to the parent branch. Okay, We use now the notation that Z is the generation 0 is the trachea. That's basically that first branch. That's the one which we which directly goes into the area where we inhale. And then we have now this geometry here. And now you can see already it's important that when we look at these vessels, that the space which is occupied by the lung is used optimally. Okay, so we would like to distribute not only, okay, if you want to distribute the capillaries which are in these alveoli, we want to distribute them kind of optimally in a space, then we also have to distribute the leaves or just the lower generation, or sorry, higher generation branches, which basically are responsible for the gas exchange. We also would like to distribute them also optimally in that space. Okay, so we would like to have an architecture which is optimal in terms of distributing the air which we inhale into this volume. Okay, that's one thing. On the other hand, there is another constraint which we will also discuss. I mean, for example, you could basically just make very narrow little branches and have many of them, and then you could get a very optimal distribution. But the problem then is that you need to have a very strong pump to basically suck the air in, because there is a resistance. I mean, we know that very well when we have a cold. Then it's usually just the upper branches which get a little bit narrower, for example, the nose. And already that makes a huge difference. It's hard for us to breathe through the nose because we cannot generate enough low pressure to basically suck the air in, and then we have to breathe through the mouth. We all know that. And of course, that becomes even more extreme if you have something like that deeper in the lung where the diameters are already much smaller. So this resistance is a big issue. So if we have too high resistance with breathing, then finally we cannot bring in enough fresh oxygen or fresh air with oxygen, and we would basically die and can become dangerous. Okay. This is just an example of a visualization of, on the left, of a human bronchial tree. These are the conducting airways. This is not showing any of these alveoli. It's really just the airways, and on the right is the rat. We can see, I mean, there are differences, but essentially the architecture is quite similar. Of course, there are differences, but it's not that we have a completely different architecture. So then again, we have here about, as I said before, about 18 to 30 generations of branches, and it is less in the rat because of course the rat has a much smaller volume for gas exchange and also needs, of course, less fresh oxygen. We can do the math. When we take 23, we take 2 to the power of 23, we get about 8 million end branches. Okay, that's the kind of the average. And that's basically called the alveolar sacs. So alveoles, we should remember that word, but then sac is just basically, because it's not the true flow, it's basically the end. It's like a sac, which basically means that air cannot go further. This is a sketch of the different generations. You see again, we start here with generation 0, with the trachea, and then we have the generations 1 to about 16. And in this part here, this is basically the conducting zone. We don't have gas exchange. So this is really that part which we consider as a rigid tube system. Okay, so this, we can really assume that this is more or less a rigid tube system. Now, this is not the case anymore down here. Now, you can imagine if it was also rigid, I mean, because the fluid at these pressure differences which we have can be considered incompressible. So we cannot say that the density of the fluid is significantly changing in the whole system. So it's essentially, you can assume constant density. So in order to really bring something in, you have to increase the volume. So when we inhale, because it's not a true flow, at the lower part of the lung, that means at the higher generations, somehow it has to expand. So there has to be some flexibility in the system, which basically makes exactly that difference when we inhale, let's say, I don't know, an endurance athlete, maybe 5 liters or something like that. Then these 5 liters, that's basically the compliance. So that's the volume which basically changes every time when he inhales and exhales. Okay. Then we can also see something else. I mean, we have now, again, generations 1 to 16. Let's just look at those first. The diameters of these branches, okay, the trachea is the thickest one, then it basically becomes thinner and thinner and thinner down to about, in this case, it's about 0.6 millimeters. And then we have the length. The length, the same thing, also becomes much smaller, about 17 millimeters. 1.7 millimeters, sorry. And then we have the number, which is just the power, as a 2 to the power of the number of generations. So you see 1 trachea, obviously, and then 2 are in the next generation, and so forth. And now interesting for us from the fluid dynamics viewpoint is the cross-sectional area. The cross-sectional area, even though the individual branches become thinner and thinner, but because of this exponential growth of the number of branches at a certain generation, the cross-sectional area at that generation level, it increases dramatically. Okay, so we have here 2.5 square centimeters in the trachea, and then at generation 16, if you take all the branches there together, it's 180 square centimeters. Now, can somebody tell me what that means for the flow? So we are still talking about that part which we consider a rigid tube system. So now we are pushing fluid at a certain, with a certain mass flow through this system. And what happens from a fluid dynamic viewpoint, which is important for us? Yes? The fluid slows down. Yes, exactly, because of the continuity equation. So we have the same mass flow that doesn't change, and then we increase the area, and then of course the velocity has to go down. And that's important for what? So when we think about Navier-Stokes equations, for example, what number is so important? Yes, exactly. So we have basically much slower velocity, and at the same time we have also in each individual branch a much smaller diameter, so the Reynolds number goes dramatically down. And what does that mean if the Reynolds number becomes very small? The flow is laminar. Exactly, yes, it's laminar. And actually in the extreme case, if the Reynolds number becomes even smaller than 1, at some point it's more than just laminar. We get the creeping flow, that's basically Stokes flow. That's basically what happens then even further down in the lung. So at the highest generations, then the inertia term doesn't matter at all anymore. Okay, but important for us, very soon we get to a Reynolds number about that generation 5, which is small enough that we can say this is really laminar flow. And then what kind of law do you know in order to compute the mass flow rate as a function of the pressure drop in a tube when we have a laminar flow in that tube? Sorry? Poisson flow, yes, exactly. And that's a very simple formula. And that one we can then use in order to describe what kind of resistance we have in these tubes. And that's what we will use in order to derive the resistance and the work which we have to do in order to breathe. Okay, so again, this is the conducting region. So this is just about distributing the air in the chest. It's about from generations 0 to 16. And then we have the, as I said, it can be considered as a system of stiff tubes, which makes our analysis quite simple because we can work with essentially, it's just a static through flow. Okay, it's only for gas transport, no gas exchange. Huh? And then we have the green part, which is the respiratory region. There it is different. We cannot say anymore that this is a system of stiff tubes for the reason I said before. So if somebody can really inhale 5 liters, that's actually where the volume has to change by 5 liters. Okay, so that's from generations 16 to the end, so in average 23. And there we also see the alveoli. It's here in this sketch kind of scene. We get here the first ones, and then very quickly we get the fully populated surface of these, it's called alveolar ducts. So it's not alveolar sacs, but duct is basically, it's still going through, and only at the very, very end, at the leaf, we talk about the alveolar sacs. Okay, and that's where the gas exchange occurs in these little bubbles. See, it's just indicated here, like here, there are the individual ones, there are these little blisters, and these blisters, they are important for the gas exchange. Okay, and I said before, this is highly distensible tissue. It has to, because this volume which we inhale, it has to go somewhere, and that's actually because the volume in these regions becomes bigger. Okay, that's an interesting thing which we actually will discuss in more depth probably in the second hour today. It is about the architecture of this binary tree, and we can now also see here something very interesting. So what we are looking at is the ratio of diameter in generation Z. And divided by the diameter in the previous generation Z-1. Okay, so that means basically by how much is the diameter reduced from one generation to the next. And we can see this here in this exponential, actually it's exponential in this direction and linear in this one. We can see that we have here a linear curve, which means that we have here an exponential decrease of this diameter. And this exponent for this exponential decrease is basically changing around the point where the respiratory region and the conducting regions meet. That's at about generation 15, 16. Huh? And then the slope changes in this exponential plot, and we can see that there must be something else describing this ratio. Okay, that's something we'll discuss later. Here again, just to kind of visualize this in a sketch. We have here this conducting region. Then we get the first alveoli here at around generation 16. There are actually even smooth muscle cells around, so smooth muscles around here. And then basically we can see that very, very quick we get a fully populated surface with alveoles, and that's called the alveolar duct. That's basically the airway which basically passes through. And then we have the endpoints, the leaves, which are called the alveolar sacs. Now there's also something interesting that all that here, when we cut it off here at about generation 15, 16, then we get something which looks like cauliflower. So that's basically this here. And this is called the pulmonary acinus. So this is, you can think if we go down to about generation 16 and we calculate how many such sacs exists. I think it's about 10,000 or some, or 30,000, just give you the number. But these are many, many of those. Huh? So at every point at about generation 16, we can cut off and we get one of these kind of cauliflower looking objects. And these are called pulmonary acinus. And they make about 90% of the total lung volume. That's important to remember. So the lung volume should be mostly used for gas exchange and not for distributing the air. And the lower generation branches, that basically the conducting region, that only occupies about 10% of the total chest volume, or lung volume, I must say. Okay, that's something which we should keep in mind. But important is that at the end, we would like to construct a air conducting tree such that not much space is used for it, because we would like to use the space for these guys. Okay, so this alveolar surface, if we integrate over all these alveoli in the lung, it's about 130 square meters, which is quite impressive. This is about a tennis court. So if you take all our alveoli and we just lay them out and make them flat, the surface would cover a tennis court. And that's quite impressive. All this area, it's a very, very thin membrane, just about 1-2 microns thick. It's basically immersed by little blood vessels, the capillaries through which the red blood cells flow, and there the gas exchange occurs. And there are about 300 million alveoli in the lung. And this is now a picture of this cauliflower, this one of these pulmonary acini. And I said before, because when we do the math, then we get about 10,000 such alveoli, and wrong. Each of them has about 10,000 alveoli, and there are about 30,000 such acini in the lung. Okay, so the product, of course, is in about 300 millions of alveoli. Okay, you see, it really looks like a cauliflower, and here it was cut off here. I think you can approximately guess here. That's the root of this acinos. That would be basically this location here. So they are, of course, small. I mean, if you have 30,000 in our lung, then each of them is very small. And this is just a cut through, and we can also see nicely in this cut. I mean, some of that looks like just a little pores, but it's not pores because when we hit by coincidence a plane in which we can follow an airway, then we can really see this kind of airway structure, this tree-like structure, which is basically just shown here. But otherwise, it looks like a sponge. Huh? And yeah, these bronchioles, they feed, of course, the alveoli. Somehow, some of these sponge-like holes, they are basically cuts through individual alveoli, and some of them, like the yellow marked one, is an airway. So let's talk about the driving force for the gas exchange quickly. It's, of course, the partial pressure, and I think that's quite common sense, and we know that very well. It's clear that then the partial pressure of oxygen is bigger in the inside of the alveoli, so where we have the air flowing. If it's higher than in the blood capillaries, then we basically have, if the membrane is transmissible to oxygen, there is basically an oxygen flux from the air compartment into the blood compartment. Okay. This is now maintained only, of course, if the partial pressure is kept high in the air part, and that's why we have to basically perfuse it at a regular rate, because otherwise, very soon the oxygen is basically drawn out of the airstream, and at some point partial pressure difference becomes too small, and there is not enough oxygen getting into the blood, and we know what happens. Then, yeah, for efficient ventilation. These alveoli are arranged around the ducts. We have seen that already. I think that also makes completely sense from an engineering viewpoint. We have to bring them, we have to maximize the exchange area and make sure that the air there is exchanged very regularly. So again, here, another sketch. Here's together with the capillaries. We can see here, for example, the arterial branch. I think you all know that here it's exactly the opposite than in the systemic circuit, that the arteries in the pulmonary circuit, they are oxygen lean, and they basically take up oxygen, and then it goes back to the heart in these veins here. Okay, but you see now in this sketch, we have here individual alveoli, and then we have this network of capillaries embedded in these membranes, and that's where we have the gas exchange. So this is basically these blood capillaries which are embedded here, and we can see these very nice pictures. This actually what we see here is a membrane. Okay, all that here is a membrane, and then we can see these red structures here. These are capillaries cut through, and then this is again just a two-dimensional cut picture. And what we can see here again, these are membranes. Okay, these are alveolar membranes. So actually here there will be air, and on this side here as well. And then we have here these embedded blood vessels with the blood cells, the red blood cells in it. And you know that the red blood cells finally, they bind oxygen to it and transport it efficiently through the system. So this is really about the scale. And we know that the red blood cells are in diameter about 5 microns, around that. And we can see that the membrane itself is much thinner. It's just thicker, where we have these embedded vessels, which are in the order of about 5 microns. And here we have more like 1 or 2 microns in thickness. Okay, so this is, it's quite amazing if you think about the scales. You have these little vessels, and this really has to work, otherwise we don't function. And there are so many, and it's such a different scale than the whole lung. It's quite an amazing device or organ. Okay, just what I said already. This is the alveolar space, and then we have the membrane between. Said before, the thickness is about 1 to 5 microns. 5 microns probably there where the vessels are located. And because that's automatically such for a capillary, it doesn't make sense that it becomes much thinner than 5 microns in diameter, because the red blood cells are about of that size, and we don't want to squeeze the red blood cells through. That wouldn't be efficient. Okay, so like that, it's ensured that there's a close contact for diffusion. I mean, if this membrane is very transmissible for oxygen, then there's a very, very short distance, and it's very efficient to take up oxygen. So let's talk more about the fluid dynamics. And we already saw that the cross-sectional area increases rapidly with higher generations, but at the same time, the diameters of the individual vessels decreases. This is now just the total area which increases. And again, when we basically think about the velocity, as somebody has said before, the velocity goes down inversely to this here, okay? Because when we look at the continuity equation for incompressible flows, or we can just say it's approximately incompressible because the density doesn't change. It's the same density essentially in the lung. And the increasing cross-sectional area means decreasing airway speed. Okay, so that means at increasing generations, we get slower and slower velocities, but at the same time, we also get smaller diameters, and the product of velocity and diameter divided by the kinematic viscosity, that's the Reynolds number. So the Reynolds number goes down for 2 reasons. For one reason, the velocity goes down and the diameter goes down. So it's really going down rapidly. Let me just quickly here draw this sketch with a human chest here. We have here the airways. Down here we have the smaller ones, which basically are populated by alveoli. That's basically marked here with this red region. Here we have the trachea. This is basically the bronchi. This is basically the mass flow rate going into the system. Okay, so this mass flow rate up to generation 16 goes through this rigid tube system. And then we can really argue exactly that way, which we did, that the velocity goes down. Further down in the lung, it's a bit different, because then the geometry is changing. So we don't have the same geometry because it's expanding. But in this kind of conducting region where we have the assumption of a rigid tube system, we can argue exactly in that way. Now let's look at the Reynolds number. As I said before, the Reynolds number for a tube is defined by the bulk velocity or the mean velocity in the tube times the diameter divided by the kinematic viscosity. It marks or basically quantifies the inertia versus viscous forces. Okay, so you know the Navier-Stokes equation has a viscous term, it has a convective term, and the convective term accounts essentially for inertia. And this is basically the scaling of the relationship. Then there is another number which is important, it's the Wormsley number. The Wormsley number also basically scales with a ratio of unstationary inertia forces and viscous forces. So in other words, if the Wormsley number is very small, then we can always work with quasi-steady flow solutions. Okay, so then the flow velocity is only changing because the boundary conditions are time dependent. But for a given boundary condition, we can assume quasi-steady conditions. So for example, if you do a simulation, the Wormsley number is very small, you can, for one state of the geometry, you can just do the simulation as a steady state simulation, and that's good enough. So that's a second number. Now we come back to that because we need both in order to make our argumentation. But first, let's now look not only at the diameters which we have basically decreasing and the total surface area or a cross-sectional area which is increasing. Now let's look at the Reynolds and Wormsley number which we can calculate from that. And we can see that in the trachea we have a high Reynolds number. So we have here probably turbulent flows usually. Huh? And also it's we cannot use a steady state solution. It's really as unsteady inertial forces. Okay, but then at least the Wormsley number goes down very quickly, and also the Reynolds number up beyond about generation 5, even when we do rigorous breathing, we have a low enough Reynolds number that we can assume laminar flow. And then we can use Poisson's law in order to estimate the resistance in the tube as a function of the mass flow. And you can see these numbers are decreasing. For example, very, very deep, the airway Reynolds number, even when we do sport, when we have to breathe more rigorously, it is very, very small. Actually, in this case, it's even creeping flow. That means that the inertia term doesn't matter anymore. Certainly, it is not turbulent. Let me just quickly finish this part on the description of the lung. So in the upper tree, as said before, it's potentially turbulent. Lower tree, we have laminar flow and predominantly quasi-steady because the Wormsley number is very small. Good, so then I would like to stop here. We will continue after break with this topic about the ventilation. We will abstract that into a mathematical optimization problem with constraints, and then we will find some surprising facts from our little mathematical exercise when we compare the values which we really see in nature, so in us, essentially. So as announced, we talk now about this ventilation part. Huh? So it's only about how the air gets distributed in the volume which we have available. And that volume should be small. It has to be clear. We are not talking about the whole volume because we are just talking about the generations 0 to about 15, 16, but we have about 23 generations in average. So this is only one part of the lung. And that's not the part of the lung where we have gas exchange. So we would like to use as little volume as possible. Okay, so because we would like to use the rest for really the gas exchange. Good, so we have that constraint. And then the other constraint is we would like to minimize the work which we have to do in order to do that, okay? And then we know that this is, of course, when we, for example, make our tubes thicker, that would reduce the resistance, but it would also increase the volume. Okay, so there is really this trade-off between volume and between resistance. And that's something which we can put into an optimization problem with constraints. And then we can do that mathematical exercise together. Okay, so ventilation in an optimal bronchial tree. Okay, and we're just talking about the generations which basically don't have alveoli on it. So we are basically more precisely talking about the generations 6 to 16. Why? Because, okay, the lower generations, that's basically the trachea, and then the first 6 generations or 5 generations. These are very, very thick branches, kind of the core of the tree. You're not talking about that one. But then everything what follows beyond generation 6 up to 16, that's now under investigation. And we have seen when we looked at the Reynolds number that beyond about generation 4, 5, the Reynolds number is small enough that we have laminar flow. So therefore we can use Poiseuille's law in order to compute the resistance as a function of the mass flow. So what are our interrogations? I mean, the first thing is we have this interplay between shape of airway tree and ventilation. And the question is, how does this shape have to be designed in order to be in some way optimal? And how can ventilation then be optimal? I mean, we have to first define what we call optimal, what kind of constraints we have, and then how can we do the optimization? There are always 3 steps. In an optimization problem, first thing you have to do is what is your cost function? What do you want to minimize, or usually it's minimization. And then what constraints do you have to fulfill? So you cannot violate these constraints. And that, of course, has an influence. And then how do you do that optimization? That's the mathematical part. So what is nature's choice? We will compare what we get with the nature's choice. And actually, that's quite interesting because the values are close. And now let's start with the assumptions. Okay, so we have these bifurcating branches, binary tree, that's clear. I think that's an assumption which we don't have to defend. And then we make the assumption that it's symmetric. So we know that the leaves, so the alveolar sacs, are at generation 18 up to 30. So there is a variation. So we are saying all are the same. So all alveolar sacs are, for example, at generation 23. And anyway, we don't talk about the alveoles here in this exercise, but we can also state the problem that all alveoli, they start at about generation 16, 17. So there's, of course, there's also a variation. Maybe in some branches, we see alveoli at generation 14, and in others about generation 18. It's not perfectly symmetric in nature. We assume it's perfectly symmetric. Okay, then let's just define the generation. We said before already generation 0 is the trachea. Then we basically just increase every time we have a bifurcation. For example, this red here would be Z equals 3, generation 3. Then the number of branches we call N, so capital N. So we just introduce now the notation. So capital N is the number of branches at generation Z, and that's always 2 to the power of Z. That's clear for a binary tree. Then the ratio, and that's important, that's actually something we would like to investigate. The ratio of branch diameters and lengths from one generation to the next is defined by this H. So for example, the diameter at generation Z over the diameter at generation before Z minus 1. Obviously, this is smaller than 1 because this diameter here is smaller than the diameter here. And what we are doing here, we assume that this ratio is the same for the diameter as for the length. That speaks that every branch is kind of a self-similar. So when we make it smaller, we make it smaller same way in the diameter and the length. Okay, there's some kind of a self-similarity assumption. Okay, it's of course smaller than 1, that's clear. And then, of course, the volume of each branch, we assume each branch is a cylinder. It's not exactly true either, but we are making this assumption. The cylinder has a volume which is pi times the length of the cylinder times the diameter squared over 4. I think that's clear. Good. Then when we assume this symmetric binary bifurcating tree, let's draw it here. We have the generations labeled with colors, with different colors. We consider generations 6 to 16 now. That's now for the remaining part of this chapter. We are always talking about generations 6 to 16. So we are still in the conducting region with generation 16, but we are excluding the lower branches where we have the higher Reynolds numbers, such that we can make this analysis. So generation, oh, okay, here I use I, sorry. That was, just have to remember, here I use I instead of Z. So here I means the generation, but you can, it could substitute Z for it. Okay, I is now the generation. So generation I, we have basically 2 to the power of I such cylinders of length Li and diameter Di. And then we have already seen that the volume can be calculated very easily, assuming this is a cylinder. Okay, then of course at the next generation, we have higher, a shorter length and a shorter, smaller diameter, but we have, of course, more of them. So N increases and that goes on like that. Okay, now the ratio of these lengths and diameters we call the homothetic reduction factor H. So let's just refer to H. H is this ratio. And when we talk about ratio HI, that means diameter at generation I over diameter at generation before I minus 1. Okay, that's basically the same for the length and for the diameter. That's our assumption which we made, that we have this self-similarity of these cylinders. Therefore, they have to basically restrict in the same way. Okay, so now because of the continuity equation, we know that the velocity is now very small because of the increasing cross-sectional area. And then from the Navier-Stokes equation, when we think about the Wormsley number, which is very small, we can actually cross out this one. Let's just assume therefore a quasi-steady flow. This comes from our analysis where we looked at the Wormsley number, which is small enough that we can justify this simplification. And then we are basically left with a steady state Navier-Stokes flow. And because it's laminar, because the Reynolds number is small enough, we have a laminar flow. We assume that we have this Poisson law, which we can use. And that simplifies, of course, the fluid dynamics tremendously. So when we look at one of these cylinders at generation I, for example, we have here a certain mass flow rate. That mass flow rate would be, of course, the mass flow rate which goes into through our trachea. Then we have to divide it by Ni, which is 2 to the power of number of generations. And then when we assume a symmetric tree, that's basically the mass flow rate which goes through one of these cylinders. Then there is a pressure drop, of course. Does somebody know why we have a pressure drop? What is the reason mathematically? What is causing that pressure drop? When we look at the Navier-Stokes equation and think about the pipe flow, what is the reason why we have a pressure drop? Yes, exactly. We have the viscosity and we have the wall shear stress. The wall shear stress, that's basically the shear stress at the wall. And that's actually where momentum is transferred from the fluid to the solid. Okay, that's why, and in order to basically, because there is a resistance, the wall shear stress, when we do a force balance, and integrate over a diameter, it cannot be that we have the same flow rate, but we should have the same flow rate because the mass flow rate is given. But if the flow is maintained and not slowing down, there must be a compensation of that basically momentum loss, and that's through the pressure gradient. That's why we have a pressure drop here. Okay. Okay, and this pressure drop in Poisson's law is proportional to the mass flow rate. And that also can be seen very clearly. The Poisson law gives us a parabolic profile. And the parabolic profile, of course, when we integrate over that parabolic profile in this axisymmetric configuration, we have to get the mass flow rate or the volumetric flow rate. And multiply it with the density, we get the mass flow rate. And that means when we increase the mass flow rate, we have just to rescale that profile by that factor. Let's say we increase the mass flow rate by a factor of 2. Then we have to rescale this profile, this parabolic profile by the same factor. And that also linearly changes the gradients at the wall. So that means the wall shear stresses also go up by the same factor. And that is why this pressure drop, which is related to the wall shear stress, also linearly scales linearly with the mass flow rate. Okay, and then there is a resistance. Okay, so we have the mass flow rate and this resistance. And the resistance obviously depends on the diameter. And actually, this is the equation which you can find in textbooks and you can also derive it. It scales, of course, linearly with the length. That's clear. I mean, we make it 2 times larger. It's like an electric resistance which you put in series. You just basically multiply with L, therefore. But then there is this d to the power of 4. And that means that if you make the diameter smaller by a factor of 2, then we have 2 to the power of 4, that's 16, right? Yeah, so we have 16 times smaller resistance in that case. So it's a very, very strong response to only small diameter changes. Okay, now let's look at the volume first. Afterwards, we will look at the resistance. So the volume of a branch at generation Z, it can be written, I leave these spaces for a good reason. We can, of course, write it as the length, as I said it before, the length times pi times d squared over 4. That's clear. And now we go to generation Z plus 1. And then we just have to basically multiply this here with this factor h. Remember again, h is the ratio of d at Z plus 1 over d at Z. So basically it cancels out this d here and multiplies it with d Z plus 1. Okay, and the same here for L. Okay, so this is now the relationship. And now just a little bit rearranging shows that the volume at the next generation is by this factor here smaller than the volume at the previous generation. Okay, so now we have essentially found the scaling very easily, the scaling of the volume. And now I think it's already clear. I mean, if you have a volume of a self-similar body, we just scale it by a factor, then because the volume is that scaling factor, must be the scaling factor to the power of 3. I think that's quite logical. Now let's look at the resistance of one of these cylinders of a branch at generation Z. We can now use this Poisson's law. I just write it down here and I do the same thing. Now I just have to multiply, when I go to Z plus 1, I have to multiply L with this reduction factor, and D also I have to multiply with this reduction factor. And now you see that the reduction factor here appears once and here to the power of 4. So that means we have here a scaling of the reduction factor to the power of -3 times the resistance at the previous generation. Okay, so now we have these 2 scalings. And now we can just look at kind of a resistor network. It's like in electrical circuits, it's exactly the same. So we have here a mass flow rate or a volume flow rate. Now we can replace it with the current. Okay, and then we basically would like to know what is the effective resistance at each generation. Okay, so we have these generations here. That would be generation Z minus 1, Z plus 1. And now we can basically come up with an equivalent network where we use these kind of parallel conductors with the resistances, and we basically compute from the parallel resistances this effective resistance. And we know that this is the harmonic mean. So the resistance, the average resistance at that generation is the harmonic mean, and the harmonic mean is basically the number of resistances of each individual branch to the power of -1. Okay, and then we have to again take the power of -1 of this. Okay, that's the harmonic average of this, or the harmonic sum. It's not the average, it's the harmonic sum. And then we can just rearrange that when we basically say that we know the resistance of branch 5, because we do this analysis for branches 6 to about 16. So we basically take branch 5 as a reference, and then we basically get from that here, we get automatically this equation here. Okay, so this is basically for branches 6 onwards up to about branch 6, generation 6 onwards to about generation 16. For the volume, we can do something very similar, just taking this equation, we can write it like that. Okay. Again, this is always here it's just a sum. Of course, the volume, we don't have to do any kind of harmonic sum. Here it's really the algebraic sum. I think that's also quite clear. So that is about volume and resistances. And now I would like to know how big is the work which we have to do. And it's like in an electric network. Somebody know how, let's say we have an electric network with resistances. How do you compute the work which you're, let's say the power which you have to do to get the current through a resistance? What is the simple law? Here it's the same, of course.
Reduction of resistance to square current.
Yeah, it's essentially the product of potential drop, and then with the current. So I times U, and that's here the same. In our case, U would be, so the delta U, so kind of the potential drop would be the delta pressure, and the current would be the Q dot. So it's exactly analogous. So we have here the dissipation, which is essentially the power, we can say, which we basically have to bring up in order to compensate for the dissipation. It's the Q dot, which will be in an electric network I, and that will be delta U, so the potential drop, which we have here. Okay, and then we can basically relate, we have seen that before, according to Poiseuille's law, we have here the total resistance multiplied with the, again, the flow rate. That's basically the pressure drop, and that gives us this very simple equation here, where we have to take the flow rate, which is in an electric circuit, the current, and then that's basically the sum of all these effective resistances, because now it's not parallel anymore. These are now in series. We can just add them up. So the effective resistance of the whole branch here, or of the whole chain here, because it's all in series, it's just a sum. Okay, so then basically we end up with this very simple equation here for the dissipation, the power which we have to bring in order to compensate for it. Okay, this is basically, yeah, it's actually a power, because this is the equation for power, but finally when we integrate it over a time, it's a work. So we would like to minimize the work which we have to do. Okay, now that means nothing else. This here we cannot minimize. The Q dot, that's given. I mean, we need a certain amount of air circulating in our lung, that's a given, but we would like to do that now efficiently. And the only way we can make it more efficient is by changing this effective resistance. That's the only way we can take influence here, or nature could take influence here. The rest is physics or biology. And now the optimization problem can be defined. So we would like to minimize this total resistance for a given tree volume. Now this tree volume omega, that's basically the space which we would like to allocate, where we are okay to allocate for this conducting region. We said we would like to keep it minimal because we would like to use most of the space for the respiratory region and not for the conducting region. Okay, so this omega should be small. So let's say we just say for a given volume omega, we would like to minimize the resistance. Okay, so we just specify that. So we say that this is the total volume specified. And now we do this minimization. So we would like to minimize the total resistance, which is equivalent to minimizing the work which we have to do. And that H, of course, is the only parameter set which we can try to figure out, or where, let's say, during evolution could have been varied. As long as we are taking this binary tree basic design, then H is basically the parameter set. And then the constraint is the total volume. The total volume matches the specified one. Omega is the specified volume. And this is basically the total volume which we get from our calculations, which depends, of course, on the choices of H6 to H16. And now, in order to solve this optimization problem, we use Lagrangian multipliers. So we are basically defining this new function which we would now like to optimize. This is the optimization problem. So we would like to minimize that under these constraints here. And I don't want to go into the details. I think I would go over the time if I did that. So I just present the result. But this is essentially the way you go about. You define your cost function, which is the total resistance, but then you have a constraint, because you can easily imagine that if these factors here would be basically even greater than 1, then the diameters would become bigger and bigger, which would be good for the resistance, but then you would use too much space. So you would like to use just an allocated space omega. That's basically the space I give to you, and you have to find now the H's which basically use the space optimally such that the resistance is minimal. And now this is just H6. That's basically that's basically where we start with, because that's the ratio of the diameter at generation 6 divided by that at generation 5. That's not in our domain of optimization. That's actually in that part which we don't want to optimize. We just want to optimize from generation 6 on. Okay, so what comes out actually is this here, that for all these reduction factors, irrespective of the generation I, it is 1/2 to the power of 1/3. That's basically the result of this optimization problem. That's for generations 7 to 16. Okay, that's the best tree in that sense. And actually something interesting. So we are stopping at generation 16. But if you did that, if you went on and you would go to infinity, so there's no upper generation. So now you would just say that I go from generation 6 or 7 up to generation infinity. The question is, would it fill that volume, or would it exceed that volume? You can easily imagine that the volume may diverge and also goes to infinity. But the interesting thing is here we have kind of a fractal object, such that when we look at the space which is then occupied, it's exactly that omega. So it converges to omega. So this spatial, or we call it fractal dimension of this object with this reduction factor, is exactly 3. Okay, So now the tree which we are forming here, because we are stopping at generation 16, does not exactly fill that that volume, but the fractal one, when you go to infinity, that one would basically fill that volume exactly. So therefore, this tree here as a fractal tree with no upper generation bound would have a dimension of exactly 3. The fractal dimension is exactly 3. Okay, so this is a space-filling tree. Okay, if you would make this reduction factor a little bit larger, in that case, it would basically diverge and would go to infinity, and otherwise you would not use this volume optimally. Okay. Yeah, this is just mentioning the names here who came up with this law. And this is basically done here by these gentlemen for blood vessels for kind of a similar problem. Now, this is just showing the curves of volume and resistance in the same plot. So we have here the blue curve, so this one here, which basically shows the increase of volume as we increase the this ratio. And this will be the increase of resistance if we reduce this ratio. Okay, so remember when we make the reduction factor here smaller and smaller, that means we basically get very quickly to very, very small diameters. That increases the resistance, but of course it also reduces the volume. Okay, and actually the value which we have found here is this here. So it's really kind of showing that it's pretty much at the point of the best compromise. Now you can easily see that when we are too much on the left and we are just changing this factor here a little bit, it would basically change the resistance dramatically. It's a very steep curve here. While on the right, the sensitivity is very small, so it would not change the resistance dramatically. And the same for the volume. If you are here too much on the right, a small change has a big impact on the volume. Okay. Okay, so the work, just to repeat, the work is, or actually the power is the mass flow rate, the power of 2 times the total resistance. And the goal is now to reduce this resistance, to minimize this resistance. And when we are here on the left, so on the left of this kind of critical value, then basically the change of the pressure drop is large and very sensitive to changes of age. So that means also that the power which we have to bring is going to be large. A change of the power which we have to basically invest is large and sensitive on changes of age. On the left, it's very insensitive. But for the volume, it's exactly the opposite. Huh? So here on the green side, we are safe in terms of work which we have to, or power which we have to bring. And here we are not safe because it's very sensitive. So if you're operating too much on the left, it's very dangerous. I mean, a small, let's say, disturbance, let's say from some illness, will have a dramatic effect on us, and then it can become dangerous. When we are more on the right, we are kind of on the safe side. I mean, whether we are here or here, it doesn't really change that much. But when we are too much on the left, it changes a lot. Okay, now let's look at the real human lung and just compare some values. I mean, we have found this, this reduction factor of 2 to the power of -1/3, which is roughly 0.79. And now let's look at the real values. Now, in the real lung, it's not so that this assumption that the reduction factor is exactly the same for the diameter and for the length, it's a little bit different. But here, look at the scale, it's relatively close. Huh? And when we compare now, for example, the length reduction factor, which are these crosses here, is pretty much constant. Of course, you have some fluctuations here. That's always, you have always noise in such systems. And in the case of the diameter reduction, it is increasing. So it basically is rather larger. And we have seen that for the resistance, it's better to have a larger value. If you have a too small value, then the resistance increases rapidly. So it's rather on the conservative side in terms of resistance. On the safe side, it's a bit larger because the real value, the value which we have computed is 0.79. That's this green line. So it seems that nature has basically converged on a value which is slightly higher than the optimal one. But when I go back here, then we can see that we are now somewhere in this range, so on the safe side. Okay, so there is margin for some disturbances due to, for example, illnesses. Okay, now, yeah, that's just a summary of this plot here. So the reduction factors for the diameter and the length are not the same, not exactly the same. The one for length is around 0.8485, so it's a bit higher than the one which we have calculated, but it's in the right range. It's larger than that one. It's approximately constant for the diameter reduction factor. It's also larger. Actually, we start here about at the same value at generation 6, but then it starts increasing when we go to the higher generations. So it's moving to the safe side with the generation. Huh? And this age of being larger than the optimal value, that is actually a good thing for a safety reason, I said before. So now we are really in this safe region where the sensitivity of the resistance on changes of these reduction factors is small. And that basically, so when our lung develops, I mean, maybe there is also in nature, there is always some randomness, some fluctuations. So there should be margin for such things that when during growth, the optimal ratio is not exactly found or reproduced, then we would be in a dangerous regime. And with the safety margin, it doesn't matter so much. This is just a normalized resistance as a function of this reduction factor. And now we can see again this, this is the dimension, the diameter reduction factor in percent. So, okay. So when we have a change in the reduction factor by 4%, that means our resistance increases from 1 to 2. So it doubles. Okay, that just shows it. This is because of this Poisson law and the whole exponential relationship here, which we have from generation to generation, that there is a very, very strong response by just changing this reduction factor, increasing it by 4%, it increases the resistance by 2. And that's, of course, dangerous if the basic resistance is already very large. Okay, and then the more we would be on the left with our reference value, the more this amplification factor would be. Okay. So then this, of course, I said before, has, of course, implications for pathological situations. And there we are glad if we are not exactly at the optimum, but more a little bit on the safe side. That means some of the volume, you can say, in our chest is wasted because it's not used optimally. And therefore, our chest has to be a little bit bigger for that in order to provide enough room for the respiratory part of the lung. But that additional volume, I think, is very well invested in order to be on the safe side. So asthma, bronchiolitis, I mean, you name it. I mean, allergic reactions. As I said, I'm not a medical doctor, so I just bring here some obvious examples. There are many, many more, of course. So these typically lead to effectively a reduction of this HT. And the length, by the way, is usually preserved. I think it's clear. It's usually the effect of some illness is stronger on the diameter than on the length. Now let me quickly summarize what we found here. So the volume which we allocate for this conducting region is larger than strictly required. So we are essentially using a little bit higher volume than we should do optimally. Okay, so the remaining volume, which is now free for the respiratory part with the alveoli, is now a little bit smaller. So therefore, overall, the chest has to be made bigger. But something what we should remember is we are talking about 3% of the overall volume. So we said that all the acini, okay, that's basically together that part which makes up the respiratory region, that makes up for about 90% of the lung. But then here we are not talking about the rest. We're just talking about generation 6 to 16. This is about 3%. Okay, if we are on the safe side, then we may use 5% instead of 3%. So it makes a little difference overall. And therefore, it is absolutely a good choice to be here a little bit on the larger volume side than necessary. Okay, the sensitivity of the resistance on H is very relevant for the robustness. And we have seen that when we are more towards the larger reduction factors, we are on the less sensitive side. So then a change doesn't really have such a strong influence on the resistance, and that's good. The design of this bronchi is basically a design of where safety is a consideration. So safety, there's a safety margin against the possible constriction. I think it's clear for us, we are engineers, we build things, we design things. When you do an optimization, it's always good to build in enough safety. I think that's obvious. We don't want to just build something as light as possible. It just has the strength needed for the standard conditions. There must just be some unexpected thing or aging of the material such that it then suddenly would break under a condition which basically hasn't been foreseen. And therefore, it's always good to be on the safe side. And I think that's how design is basically guided. It's not only by optimization, it's always by also building in some safety margin. So the optimal airway design would be dangerous. It's like building an airplane optimally light. I have a friend who bought a bicycle, kind of a custom-made bike, very expensive, super light, and then it just broke in parts when he was riding. So that was not enough safety margin in that bike frame. So I think it's clear we shouldn't construct things like that. Yeah, so I'm actually at the end of this lecture today. So next time we will talk about gas exchange.